In this video, we're going to start looking at how finite elements are formulated. We're going to focus initially on a bar element, and we're going to use basic equilibrium equations to develop a system of equations that we can use to solve for eventually a truss structure, but initially now just a bar element. Before we begin, let's go back and think about the things that were developed in Lesson 2. We developed equations that related stress and strain and strain and displacement in 2 dimensions. And then we represented those relationships as matrix equations. So first off, the relationship between strain and displacement can be captured by this equation shown here, where the matrix is actually a partial derivative matrix operator, and it uses the symbol, just the partial derivative symbol in the simple form. The second major equation that we developed was the relationship between stress and strain. And this was the particular one for isotropic plane stress. If you had plane strain, the equation would be different. If it was non-isotropic, then it would be more complicated as well. So those are our 2 fundamental equations. And let's pause for just a moment and think about what this means. It's going to allow us, if we can come up with a method to find displacements inside of a material, we can then go from those local displacements to find the local stresses and strains inside the part. So as well, let's do a quick review of the overall process involved in finite element analysis. You start out by taking a complicated problem and breaking it into a number of small pieces. We break it into a limited number, a finite number, not an infinite number. And those pieces we call elements. We then find a stiffness for each one of those elements. And by stiffness, what I mean is we establish the relationship between all of the potential loads that act on the element and all of the potential displacements in the element. And I'll get a little bit more specific in a few moments about that. We're not going to look at displacement throughout the element. We're actually going to look at specific locations in the element. We call them nodes. So a matrix form of that equation is F equals KD. Once you've done this for every single element in your structure, you then need to use continuity equations, equations that ensure that the material doesn't rip or overlap, in order to link the loads and displacements between the elements. We'll go through this a little bit later, but what happens is we end up with a larger system of equations represented by a global stiffness matrix, a global set of displacements at nodes, and a global set of forces at nodes. Next, we apply some boundary conditions, some constraints that tie the geometry down in space. So a boundary condition is defined to be a specified displacement. And then finally, we can use this global system equation and invert the stiffness matrix in order to solve for the unknown displacements. And once we've done that, we can go back, take all the displacements at the nodes, and again, remember, now that we have displacements, we can find stresses and strains. Before we get into the details of formulating finite element analysis for a bar element, I just want to talk briefly about the conceptual model that we're doing here. We are defining something about the world. We're looking at loads and displacements, and that's our focus in FEA. That should seem familiar to most of you. That's what we do in spring analysis. So what are we conceptually saying about the world? Well, it's kind of like the movie The Matrix. We are redefining the physical world in terms of a system, large numbers of springs. Rather than computer code, in the Matrix movie, we're using springs in the stiffness matrix in FEA. All right, enough about the background. Let's formulate the finite element system for a bar. We have a bar here of area, cross-sectional area A and length L. Let's assume that I can treat this as a finite element. So what would that look like? So we need to first off identify the nodes of my element. Nodes 1 and 2 are going to be at each end of the bar. And I'm going to assign my axis. Then for finite element analysis, I'm going to deal with forces and with displacements, and those are going to be acting at nodes. So I'm going to have a force F1 acting at node 1 and a force F2 acting at node 2, and also in FEA, the forces and the displacements are defined positively with respect to the coordinate system. So both of these are positive forces acting to the right. In addition, I'm going to have some unknown currently displacements. Displacement 1 at node 1 and displacement 2 at node 2. So in order to develop the finite element model of this bar, I'm going to cut it in half, and then we're going to look at equilibrium of the two halves. So first off, I cut it in half. Well, what do I have to do to maintain equilibrium? I need to look at the internal stress state. Now, stresses, unlike nodal forces, are defined as positive when they're acting outward from the system. So sigma A on the left part is acting to the right, sigma A on the right part is acting to the left. Write my sum of forces for the left. I know that the sum of forces in the x direction is equal to 0, and that's just F1 plus sigma A. On the right side, that is negative sigma A plus F2 is equal to 0. Let's apply my constitutive law, or my material properties here. I'm going to assume linear elasticity, so sigma, and it's a uniaxial system, so I've just got a sigma x and an epsilon x. Sigma is equal to E epsilon, and then that's going to simplify my two equations as shown. Now let's apply the compatibility equation, or the strain-displacement relationship. So epsilon is equal to the derivative of displacement, the displacement variable u, with respect to position x. This, by the way, notice it's not a partial derivative because x is the only independent variable. When I apply that, I get two differential equations. Now, in order to solve these differential equations, I need to make an assumption. This is critical. This is fundamental to FEA. We assume something about the displacement field. If you'll recall, this was one of the limitations I identified for FEA. Typically, what we do for a bar element is we assume a linear displacement field. So I can describe the displacement field u as some constant a0 plus a1x. If I were to then plot that, I'd be saying this is my linear displacement field between the d1 and the d2. Continuing the derivation, let's find these constants, a0 and a1, in terms of the unknown displacements at the nodes, d1 and d2. So to find those, we start out by saying that u of 0 is a0, and that also corresponds to d1. U of L is a0 plus a1L, and that's d2. So together, these give us expressions for a0 and a1. I can plug them back into the expression for u of x, and then I'm going to rearrange terms as you see here. So u of x is equal to 1 minus x over L times d1 plus x over L times d2. I can write those two coefficients for d1 and d2 as n1 and n2. Now, why am I doing this? Because in FEA we want forces and we want nodal displacements. So d1 and d2 are the nodal displacements. The coefficients of them are something new that I'm calling shape functions. These have an important characteristic in FEA. We're going to use them for all types of elements. In this case, we can see that shape function 1 has a value of 1 over at the left border of my element and a value of 0 at the right side. Similarly, n2 has a value of 0 on the left side and a value of 1 at the right side. And these are common properties. I'll talk about properties of shape functions in just a moment. Moving forward, I can write the expression for u in terms of a product of a row matrix with the column vector d1, d2, and I can simplify that expression to say u of x equals n times d. We're going to see a lot of this in FEA, keeping things compact with these reduced forms of equations, but you want to keep track of what they're referring to. So in particular for a bar element, the n matrix is the two shape functions that I've defined here, and this is true for all linear bar elements. Let's finish up this bar finite element formulation. I now have my displacement field assumption. U of x is equal to the shape function 1 times displacement 1 plus shape function 2 times displacement 2. I now have an expression for u, so I can take it back to my differential equation of equilibrium and take the derivative of u with respect to x. That's going to be the same in each equation. And then I can simplify that expression and put these two equations into a matrix. So notice what I have here. I have a force vector on the left-hand side giving me the forces at nodes 1 and 2. That's equal to a matrix multiplied by my displacements at nodes 1 and 2. The matrix in the middle here is what we call the stiffness matrix, and that makes sense. It has units of stiffness. So F equals KD is the is the matrix equation for finite element analysis for this bar element. F equals KD is going to be the same expression for every finite element. The specifics that change for each element type are which displacements we're looking at and which stiffness matrix we have as a result.